So one of the topics for today is this whole idea of thermoregulation or heat regulation of your body. And it's one of the examples of homeostasis, which is simply the balance that your body needs to make sure it has. So if things get a little bit out of balance, your body is very quickly going to adjust things to make it so that it goes back into proper balance. So you see a picture in front of you, and what I would like you to do very quickly is I would like you to try to explain what's going on. And I don't want you just simply to say here, oh, he's sweating. I want you to kind of think of the physiological changes that are happening in the body to make this happen. And then tell me a little bit about why that's happening. Here's a couple of things just to note before we start. This is an example of hyperthermia. Now, most of you know about hypothermia, but this is kind of hyperthermia. And hyperthermia is this whole idea that the core body temperature is rising. It's getting warmer than it should. So here's a nice little diagram. You can thank me for my drawing ability later. There's a nice little drawing kind of showing when we say the core of the body, what are we actually talking about? And the red here kind of indicates where in the body would be considered the core. So it's the area around your organs, your heart, your lung, your kidneys, your liver, that's your core. Your brain would be considered a core of the body. And your body desperately wants to keep that temperature right around 37 degrees Celsius. So that's kind of considered to be normal body temperature for your core. And when this goes up, you have hyperthermia. When you have a fever, that's one example. But when you exercise sometimes, your core temperature is going to start rising as well. So what I want you to do here is explain this picture a minute. I want you to write it down. I want you to tell me why, or actually what's going on to have this scenario of this person sweating happen. If you need to take a look in your book, page 300, and I think it's 333 is an excellent page. Okay. So here's a little diagram I think that at least tells part of the story for this whole idea of regulation of hyperthermia. So you can kind of look here, we've got muscular activity going on. When your muscles work, they produce a lot of heat. That's going to start warming up the core. So in this diagram, after the body starts to warm up in the core, this hypothalamus, this regulatory part of your brain, senses that the heat is coming up, and so it's going to try to maintain homeostasis. And so what it will do, it will stimulate the sweat glands to start producing sweat. And that sweat then, when it's on the surface of your skin, will evaporate and take heat with it. That's what evaporation does. It removes heat. One of the things that we should probably mention here is that these blood vessels in the skin, on the surface of the skin, they will dilate. And that's really important, meaning open up. And that's really important because now blood is going to go to the surface and it'll bring that heat with it. And then the evaporation will remove the heat, and then that blood will return to the core of your body cooler than it was when it came. It's like a radiator in a car, basically kind of the same idea. So there's a couple of important things that are going on there with this cooling the body when it's too warm. So here's a scenario that's just the opposite of hyperthermia. This is hypothermia, and this is where the core of your temperature starts to decrease below 37. And I'm guessing that most of you have had a slight dip in your core body temperature from time to time. I'd like you to explain how your body does that. How does it warm itself up again? So I'll give you a couple of minutes to try that. So a little bit about the shivering here. I think it's been said that when you shiver for 15 minutes, it's the equivalent to chopping wood for about the same amount of time. And you think about how warm you get when you chop wood vigorously. Shivering is a great way for your body to warm up. So it's making all these muscles work and that sort of thing. So that's one of the things your body does. So the sensors in your skin say we're cooling down. They send a message to your hypothalamus, time to warm up. One of the things it does is shiver. The second it does is causes goosebumps, which will trap air on the surface of the skin, which will help warm you up. And then the third one is that it'll keep your vessels to your skin constricted. Now, I'll just share a little story to kind of illustrate this point. When I did winter camp, quite often somebody would come to me and say, my feet are really cold, Mr. Pierce. And I would look at them, and the first thing I would look at is, are they wearing a toque? And if they weren't, then I would say, well, put a toque on. And they'd say, no, 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 you don't understand, Mr. Pierce. It's not my head that's cold, it's my feet. I'd say, put a toque on. And if you understand how your body deals with cold, you would understand why that's good advice. Because when their head was exposed to the air, they were losing a lot of heat. Their core temperature was going down. And the first thing your body does then is it makes a decision. It says, I can live without a few toes. I can't live without my liver, my stomach, my lungs. So I'm going to constrict all those blood vessels to the extremities, to the fingers and the toes and the feet and the hands. And I'm going to send way more blood inside where it's nice and warm to kind of keep that temperature up. Because if blood goes to the extremities, to the surface, heat's going to lose and you're going to actually get colder and colder and colder. So putting a toque on keeps the heat in. Now maybe some blood can start flowing back to the feet. Maybe those blood vessels will open up. So if you're ever outside and it's not wet feet, it's just cold feet, and you don't have anything in your head, put a toque on. It'll probably warm your feet up. Here's a good little kind of graphic of that. So temperature, decreased blood and skin temperature, number one. Impulses go to the hypothalamus, and then the hypothalamus says, okay, we're going to do three things. We're going to constrict the blood vessels going to the skin. We're going to make you shiver like crazy. And the one not on here is the goosebumps one, but that also helps. If there's one chart that I might copy down, it would be this one. I think this is no, we don't have to copy all of it down. We just have to, I think, copy down the colored words, because they kind of summarize, I think, really nicely what's going on and how your body kind of regulates this heat and maintains homeostasis. So here. So the next topic is just a topic about fluid exchange, and kind of to put it simply, it's about how does the fluid that is in your blood, that's carrying things like glucose and oxygen and vitamins, and how does that get out of your blood and into cells? And then how does the stuff that is going on in cells that your body wants to get rid of, how does that get out? Now, we talked a little bit about this in the respiratory system, but this is a little bit more of a detailed answer. So I've put on the board here kind of a typical question, and it's this. Explain how glucose gets from the blood into the cells. Make sure in your answer you use osmotic pressure, fluid pressure, and blood proteins. So we're going to answer that question at the end of this class. And I want you to put some of the stuff that we're talking about into that answer there. So it's a little bit more detailed than what we've been doing. So the first thing we should talk about here, so you have this handout in front of you, and you can write all over it, and if you want to even go on to the back and keep some notes there, that's fine. We should start by talking about this one right here. So you will notice on this diagram that there is something mentioned called fluid pressure. On one side of this blood vessel, we've got a 35 millimeters of mercury pressure, and on the other side, we've got 15 millimeters of mercury pressure. So just to kind of set this up for you, we have blood flowing into an arteriole from the heart. So there might have been even an artery here. and blood is flowing into this. So maybe this is your bicep muscle, and you're in the gym and you're doing curls and you need some more blood there to deliver, say, oxygen and make sure that that muscle works. So now blood's going to start flowing through through these capillaries and working their way through, and then eventually that blood's going to get to the other side of this capillary bed, and then eventually they're all going to join up into a venule, and then we might have a vein over here, and that will take that blood back to the heart. So that's kind of what that picture is showing. What's fluid pressure? Any thoughts on that? Well, what does it sound like? It's the pressure of the fluid in here, which is the blood. So really another word for fluid pressure is blood pressure. Now take a look at how the number has dropped. Okay? When we were talking about blood pressure yesterday and measuring it, we were talking about numbers like 120/80. And now we're down to 35 on the kind of the arterial side of this diagram, and on the other side even less. We're down to 15 millimeters of mercury. So here's a big question. Why does fluid pressure change so much? So to kind of give you a hint at that, grab your textbook and take a look at page 329 a minute. Page 329 should give you a good hint about why these pressures change. So if you looked at that picture, you will see on page 329, figure 2, you will see that the answer about how fluid changes, fluid pressure changes, is it's all about distance from the heart. In other words, as blood vessels get further and further away from the heart, the pressure that the heart has the ability to put on these vessels goes down and down and down. It's kind of like if you had a garden hose that was, let's say, 1 kilometer long, you hooked it to your house and you turned on the tap and you measured the pressure of the water right when it comes out of the tap, and then compared it to the pressure a kilometer away as this water has flowed through this hose. Where would you see the bigger pressure? Well, right by the house. Okay, because as this blood flows through, it has to fight through, these blood vessels, and that's going to slow it down, and the resistance starts to increase and all the rest of it. So the simple of it is that as things get further and further away, as blood vessels get further and further away from the heart, the fluid pressure goes down. So the second kind of pressure here is osmotic pressure. So here you'll see osmotic pressure, and the one thing you notice about osmotic pressure in this diagram is it doesn't change. The osmotic pressure is exactly the same. Now you're wondering, well, what's osmotic pressure? Well, osmotic pressure, I'm going to kind of write it like this. It's the pulling power of the solutes in the blood. Okay? So it's kind of this pressure that the solutes in the blood use to pull the water back into the blood. Okay, so it's kind of pulling power. So this little diagram, this little interaction video might help you understand osmotic pressure. So I'm just going to close this a minute, close that a minute, and let's go to this. So see if you can kind of follow what's going on here. So these I'll just get to the start here. So these bags here represent blood vessels, and these are solutes that you might find in the blood. So so what we're going to do is we're going to fill up these bags with different solutes. So the red ones here are called albumins. And albumins are simply blood proteins, and we'll talk about those in a minute. So we put 2 cups of albumins into our blood vessel, and here we're dumping in some sodium, which is salt, and here we'll dump in some glucose and fill that bag up. In bag B, in this blood vessel here, we're going to only put half as much. So here's 1 cup of albumins, 1 cup of sodium, and 1 cup of glucose. Now the question would become this: which blood vessel now has greater osmotic pressure? A or B? It would be A. Since there's twice as much solute in A, and osmotic pressure is the pulling power of the solute, bag A is going to want to pull in a lot more water than B. Now last year we talked about hypertonic and hypotonic, and so this would be hypertonic compared to this, and so more water would flow into the one that's more hypertonic. This is just a different way of thinking about that. If hypertonic and hypotonic work better for you, stick with that. It simply means that bag A will absorb more water than bag B. So if you take a look here, we can actually do that. So we're going to put bag A in the water and bag B in the water, and then we'll measure it with our measuring cup. We'll squish it out. And you can, it all goes in. It's amazing. And so there you can see that cup A took in 90 millimeters of water. Cup B took in 45. So cup A, blood vessel A, would have a higher osmotic pressure because there's more solutes drawing in the water. Okay, so that hopefully gets you thinking a little bit about this osmotic pressure. So if we go back to this other diagram again. Let's just pause. So if you take a look here then, what this is saying is the drawing power of water back into the blood vessels never change. In other words, there must be some solutes that stay in the blood vessels that never leave, that are going to create this constant osmotic pressure no matter where you are in there. There's always going to be something in there drawing the water back in. So let's go down to here a minute. This is actually by far the most important part of this. Do you understand what's happening? So we're going to look at the arterial end first. At the arterial end, notice how the pressure changes are different from each other. So in this one, the osmotic pressure is 25, so there's some solutes in the blood that don't leave that create an osmotic pressure of 25 millimeters of mercury, but the fluid pressure is quite a bit larger than the osmotic pressure. So the fluid pressure, the pressure on the outside pushing out on the walls of the arteries, are bigger than the osmotic pressure pulling the stuff back in. So what do you think is going to happen to the water and all of the things dissolved in the water that can fit through the walls of the capillary? What do you think is going to happen? It's going to leave. So so stuff's going to really start coming out here. Wherever the pressure of the fluid is greater than the pressure, the osmotic pressure pulling in, things are going to leave. Well, what's going to leave? Well, a lot of water is going to leave. Oxygen is going to leave. Vitamins are going to leave. Glucose is going to leave. Because all of those things are small enough to get through the capillary walls and head on out. And where are they going? Well, maybe you've got a cell up here. And so these things will move out and then diffuse into the cells. Okay, glucose is going to head into the cell and all the rest of it. One thing just to mention is, what's this space between the capillaries and the cells called? Well, that's called extracellular fluid. And your textbook calls it ECF. And all that is it just your cells are bathed in kind of this water, mostly water. Okay? And so this stuff in the blood, it's kind of weird. Your blood is giving away most of its water here. and it's giving away glucose here, and all the things dissolved in the water. It's all coming out of the blood vessels here. Why? Because the fluid pressure is greater than the osmotic pressure. There's a net pressure out here. Now, down at the bottom, it says, of this little diagram, it says the absorption is minus 10 millimeters of mercury. I'm just going to add something here. I'm going to say the filtration is plus 10 millimeters of mercury. And now you're probably saying, okay, well, what is filtration and what is absorption? Well, when things leave, so here's water leaving right here. When things leave the blood vessels, that's called filtration. And in a minute, we'll talk about absorption, but absorption is when things come back into the blood vessels. So we have a filtration of plus 10 millimeters of mercury here. In other words, the pressure on this part right here, the fluid pressure is greater than the osmotic pressure, and so things are going to come out. Water is going to come out, and all these other things are going to come out of the blood vessels right there. So on the other side of this capillary bed, so on the venule side, you can see that something slightly different is happening. Notice that the osmotic pressure isn't changing, so there still must be some solutes in the blood that are creating this pulling. But look what's happened to the fluid pressure. The fluid pressure has gone way down now. And so there's now a greater greater pulling in force right here. This is the pulling in. Then there is a pushing out. There's more pressure pulling in than there is pushing out. And so here, things are going to start returning into the blood, returning into the blood, returning into the blood. So what's going to return into the blood here? Well, we better get a lot of our water back that we allowed to leave here. So water is going to turn in. Hey, how about some carbon dioxide? Shall we get some carbon dioxide in there? Well, why not? I mean, we had a cell over here, and oxygen went in, carbon dioxide went out. That carbon dioxide better find its way into the bloodstream so that we can breathe it out. So things are going to return kind of wherever this pressure allows for it to return, wherever that happens, and things are going to start returning in to the blood there. And so really, here we could write down the filtration is minus 10 millimeters of mercury here. So that kind of explains why things come out and things go into your bloodstream. And it's all about the pressure differences between those. So here, I just think it's worthwhile mentioning that when you're talking about these capillary beds and so on, they're actually controlled by sphincters. So again, maybe you want to draw this in your notes, I'm not sure. But here's an artery, we've got blood flowing. Here's an artery, we've got blood flowing that way. And then right here, we have an arteriole. And I want you just to notice for a minute what's wrapped around this arteriole. Well, there's these sphincters, these muscles that can control whether blood goes into this capillary bed or not. Now, yesterday we talked about the fact that if every blood vessel in your body was wide open, you need about 200 liters of blood to fill them all. You only have about 5 liters of blood, which kind of tells you that the majority of your blood vessels, even right now as you sit in your desks, the sphincters have closed off a lot of these blood vessels so that blood's not actually flowing there. It's closed it down. There may be a small trickle of blood through here just to keep these cells alive, but they're not working very hard. They're not doing very much. So you kind of understand that that's taking place there. So if on a test I asked you this question, and I said, is that an arteriole or a venule? Your answer would be, that's in our arterial right here. How would you know? Where's the sphincters? Your body won't even let blood into this area. There's no sense letting blood in and then having the sphincter over here to not let it out again. That wouldn't make any sense. So don't let it in the first place so that it can't drop off unnecessary oxygen and good things to those cells, because those cells don't need it right now. So take a good look, kind of understand the anatomy that's going on. So on this slide here, I think we need to just talk about why osmotic pressure never changes. So take a good look here. How much? Half liter. So here you have an arterial. Here's the arterial end. Here's the venule end. The capillaries would be, somewhere in the middle. You can see that the osmotic pressure doesn't change, but you can see that the blood pressure is changing. Now, I just want to talk about these things for a minute. So in this blood vessel, you have water, of course. You would have glucose. You would have oxygen over kind of on this side. But you also have these blood proteins. And it's these blood proteins, these albumins, that are responsible for making sure that the osmotic pressure doesn't change. So what are they? Well, I'll put them in green here. They're really big cell or big molecules that are too big to escape through the walls of the capillaries. They would have a hard time getting through there. And so when those blood proteins stay in your blood, it means that the osmotic pressure is relatively constant. It's not going to vary too much. Now, occasionally, one will squeak out. Okay, occasionally a blood protein may leave the blood vessels. Why is that a bad thing? What would that create now? It would lower the what? It would lower the osmotic pressure. So now maybe this is dropped down, and if it ever drops below the blood pressure, so let's say it dropped to 14 millimeters of mercury, now it would be really hard for fluids to return to the blood, and that would be bad. That would create something like this. I'll just show you this. So here's a terrible picture. There's a young child starving. Luckily has some food here, but you can tell this person is starving. What is the telltale sign of a small child that's starving? They look bloated. They have a protruding stomach. They just look bloated. Their arms are always thin, their legs are thin, but they have this big stomach. Well, what is actually happening there? Well, let's kind of trace this a minute. So if you need energy from your food, what's the first thing you use? Glucose. If you've used up all your glucose, you use up glycogen. If you've used all your glycogen up, you now start to use up fats. And for most of us, that's not a problem. We've got energy, a lot of energy stored in our fats. Most of us could stand to lose a few pounds because we've got extra fat there. But this person here has used up all the glucose, has used up all the glycogen, has used up all the fat. So what's the last resort for this person? The last nutrient available, protein. This person is now going to start using protein for food. So if we go back to this thing here, what did we call these? What did we call these green dots? These are proteins. So that person is going to start to burn these blood proteins for fuel, and what's going to happen? Well, this osmotic pressure, because they've actually metabolized them now and used them for food, this has decreased the osmotic pressure. So now what's not getting back in? Okay, water is not able to get back in. So where's the water staying? around the tissues in the body. And so this starving child here looks bloated because the fluid around the organs hasn't returned to the blood, which has made it, you know, that kind of that bloated look. The same thing happens when you sprain an ankle. Well, not quite, but kind of the same mechanism. When you sprain an ankle, if we kind of go back to this, what happens? Well, you sprain an ankle, you break some blood vessels. Okay, you got it. Now, you know, you may be torn. Well, some of these blood proteins are going to leave. Okay, and so you've decreased the osmotic pressure around your ankle and all those blood vessels around your ankle. So what's going to happen now? Well, the fluids aren't going to return into the blood vessels around your ankle, so your ankle's going to swell. You're going to get this inflammatory thing. The other thing that's going to happen is these blood vessels get bigger. They inflame. And so now there are some spaces for these albumins, these blood proteins, to disappear. And so all of a sudden, you have a swelling issue around your ankle because the fluids can't return into your bloodstream. So what's one of the things you do when you have an injury? You put ice on it. Well, why? Because ice will bring these blood vessels back to their normal size, and then one of the things that won't be able to escape are these albumins, and so now the osmotic pressure will come up and some of this fluid can start to return. So when you have a swollen ankle or any inflammation, a lot of times the swelling is caused by all of these albumins that are leaving. So one of the last kind of little bits of this whole topic is, so when these blood proteins leave the blood, how do they get back into the blood? And the answer there is they get back through the lymph system. Now, we've talked about the lymph system before. We talked about it when we talked about fats getting into the bloodstream, and we mentioned that fat molecules were too big to get into the blood by the capillaries, and so they went into the lymph system, and then they got dumped into the bloodstream by the right and left, what are they called? Thoracic cavity there. So here's a good little picture, and you can kind of see, here's a capillary bed right here. So there's an artery, an arterial, and then a capillary bed. And you notice these green vessels there, those are lymph vessels. So watch how the lymph vessels can return these blood proteins. I'll just let this thing run.
The lymphatic system consists of lymph vessels and lymphoid organs. Lymph capillaries thread through capillary beds. Fluid and plasma proteins that leak out of the capillaries enter the tips of lymph capillaries. The lymph capillaries merge into larger lymph vessels. Lymph nodes occur at intervals along the vessels. As fluid trickles through a lymph node, arrays of white blood cells monitor it for invaders. If they encounter a foreign antigen, they call up a rapid immune response. The filtered lymph fluid passes into larger lymphatic ducts, which carry it back to the circulatory system. The tonsils, thymus, and spleen are lymphoid organs. Lymphocytes in the tonsils protect against inhaled microorganisms. Immature T cells differentiate and acquire their unique receptors in the thymus. The spleen filters pathogens and used-up blood cells from the blood and is a major site of antibody production. Now let's check what you have learned.
So just a quick mention of what the lymph system will do in this whole fluid exchange kind of topic. So any of that extracellular fluid that didn't get back into the bloodstream is going to go into the lymph system, and the lymph system is going to return that extracellular fluid to the circulatory system. That happens right in this thoracic duct right there, the left and right subclavian veins. While your body's doing that, it's almost like it thinks, well, I may as well do another job at the same time. So it's going to clean anything that was in the blood that maybe isn't good. So maybe your blood is carrying a virus, as an example, or a bacteria that needs to be cleaned out. Well, your lymph system will do that. There's a lot of white blood cells in your lymph system that will attack these things and take care of them. That's also an important one, this number 3, returning those blood proteins that leaked out somehow. We want to get those back into the blood. And then don't forget from our digestive system that one of the things the lymph system also does is it returns fats to the circulatory system, or that's the way the fats get into the circulatory system. So this lymph system is pretty important. You'll notice there's lots of lymph nodes. That's where a lot of these white blood cells are hanging out to clean and kill things that are in your blood that shouldn't be. And it does a good job kind of helping with this whole fluid exchange.